Yeah, definitely. Oh yeah. So instead
The
of
largest sign is 7.
Yeah. So we said the same thing.
Bonus is the bottom. Yeah. I don't know how. It just doesn't happen to be this section of the lecture. It just happened to be.
I was talking about before class. I was like, make sure to write that. Realistically, it's 340. And then we got bonus on top. So it's an easy one. I think I got all of it. Just printed the wrong test. So
Just harder easy.
because she messed up and printed everything.
No. She hands out, she goes, oh, that's the summer exam. Like that she gave me through like second shot. So one of the kids in the back goes, oh, there's no pressing. It's like, alright, I'll be right back.
Y'all have to fill in the blanks. Our fill in the blanks.
There's a code section.
You get 100.
Yeah, I mean, after the 3 free points and some bonus especially, it should be an easy thing.
That won't be. She grinds.
I was just going to be like, this is pressing. There are no seats. All right, I'm gonna go.
Hey, I got Shaq's. They left their glasses. For a fixed point current. Wait for this microphone.
I think I got.
They've been using a binder clip. They've been using a binder clip.
I know, but it's not here. It's just working really hard.
There's a couple on there that's like that. I don't think
Can you do me a favor? And somebody, can you go get some batteries? These are dead, and find a little binder clip so I can clip it on. All right? You just go to the, you know where the main office is? During, you know, go to the main office and ask.
All right, class, I gave you some electrostatics now. If you have any questions related to that, I'll take them right now. I'll try to speak loud. Is she recording?
Yeah.
So. I wish you did. questions at all? Class? Anything at all? Now, you've had electrostatics. You can get very comfortable thinking, I've got this. I warn you, there are some things that we're going to be covering that you haven't covered, and you can fool yourself with a false sense of confidence. So please do the homework. Just be honest with me. How many tried the homework? A couple of you. You have any questions at all? Anybody? Nothing at all? Did you get it all?
I just started.
We should probably do at least one problem, just based on my general sense of the class's understanding. You haven't even tried it. You got one for me or not? I can take it. Try to bubble this up. I warn you. You think you got it, and all of a sudden the bottom falls out. Let's just do this one. This will get us going. So problem 3A, they say they got a 20 nanocoulomb point charge at 0, 0, minus 3. So this problem, this is problem 3A. So what they've got is, this is an XYZ coordinate system. Well, actually, yeah, this is it. And they say they have a charge down here at minus 3, so it's Z equals minus 3 right here. And the value of that charge is 20 nanocoulombs. And so this is this charge down here, I'll call it Q1, is 20 nanocoulombs, all right? Now, their question is this: where do I put a charge of 10 nanocoulombs so that the field at the origin is 0?
No luck. Yes.
Just like that. No, that's all. Can you all hear me okay? All right. That's the main thing. I think if you can hear me, you can kind of follow along if you're watching the video. If you can hear me and you can see that, are you recording it here?
Yeah.
I won't throw markers there. Anyway, if you're down here, here's the deal. Now, the electric field from this one, does everybody understand that the electric field from this one at the origin right here, that's what they wanted. Just help me out here. You know it's going to be proportional to charge, so it's proportional. I'll write down the general formula. It's Q. In this case, it's going to be Q1 over 4 pi epsilon naught R squared in the AR direction. That's the general form. You all agree with that, class? Can you all see it? General form. Now we put in specific values. So for this one, they have a charge here of 20 nanocoulombs. That's 20 times 10 to the minus 9 coulombs. It's over 4 pi epsilon naught here. Now we need R. This is the vector R. It goes from here to here. So the vector R has no Y, no Z differences. Do you all follow me? The way you get a vector is you take the point of observation that you want the vector at, which is at 0, 0, 0, and then you subtract the coordinates here with the appropriate unit vector association. So you got 0x, 0, 0, 0, 0. Then you have 0y difference. And then you're going to have 0z minus ay, minus z, or plus 3. Do you all follow me on this? So it's 3ax. This vector r is 3ax. Or I mean az, or az. You all follow me on this? And just think about it. It points from the source or the charge to the point of observation of the electric field. It goes from here to here. It's pointing up. It has a vector length of 3. Anytime you're talking about vectors, they have magnitude and direction. You all follow me, class? Just show of hands. I mean, I know it's Friday, but show a little life here. Okay, we've got that, right? Now, what's a unit vector in this direction? Class? Just take magnitude, or just take r, right? Over magnitude of r. That's just az. Does everybody follow me? A unit vector has to have a total length of 1.
So if it had x, y, and z coordinates, you'd square the coefficients of ax, ay, and az, add them together, take the square root, and if it's not 1, you got a problem. Does everybody follow me on this, class? All right, now that means this, I left it as epsilon naught here, r squared, I'll just put it as 3 squared, right? Or I can put 9 down here, but you all understand that's r. If we square it, because it's going to be the magnitude squared, we get 9, and then it's in the AR direction, so it's AZ. That's the value of the electric field at this point. Where do you locate a charge so that the total, and the charge value is what? 10 nanocoulombs. Isn't that right, class? Take a look at the problem. So where will we put 10 nanocoulombs? This is 20. Where do we locate it so the total electric field here would be 0? Well, you're guessing in the right direction. What you would do is take this value of electric field and make it negative, right? Because we want to make sure when we add the electric field from the charge, the 10, it will nullify this. Do y'all follow me? Yes. So what we do is we're going to say minus 20 times 10 to the minus 9 over 4 pi epsilon naught. And whatever this r is, I'll call it r2 squared in the AR2 direction. I'm sorry. Let me do it this way. I'm getting ahead of myself. Epsilon naught times 9, and the AZ direction has to be equal to the charge, which now the charge that we're saying is going to be 10 nanocoulombs. You'll see this in a second. Some of you already see it, 4 pi epsilon naught. And now it's going to be over, call it R2 squared in the AR2 direction. So we know, now the one thing I've done is, remember, I don't know where this is, but you're going to see it in a second. This is what this electric field has to be from the second charge. Do you agree? So it'll nullify the first component, right? Now look here, you can cancel I can't you, class, just by looking. Y'all agree I can get rid of 4 pi epsilon naught right off the bat? Y'all see it in the back? All right, so I'm going to. Now after that, you see I've got 20, minus 20, and 10 nanocoulombs. All right, let me get rid of nanocoulombs first. So get rid of that. Now I got 10, 20, divided by 10. Now I have minus 2, right? Y'all with me? I'll just get rid of that totally. Now, I think you got it. I need something that has, if you think about this, is minus AZ right here, right? So AR has to have a minus AZ sense. It means the charge, since it's positive, the second charge is going to be up here, right? This would be, this is the 10 nanocoulomb charge. And we know that if it's a positive charge, we'll have a negative electric field sense. Do y'all follow me on this, class? How many do? I don't want to belabor this. Do y'all see it? Anybody not see this? It's really straightforward. So how do I get the value of this? I know the charge is going to be at a positive value of Z, right? So what's the real key to this? Well, R2 would be 1. R2 is going to be some positive value, really, right? So it's going to be some Z2, right? That's what it is. And you might say it's going to be Z, I shouldn't say R2, the location is going to be at Z2, my bad. And that means this vector direction, R2, would be 0 minus that, or it'll be minus Z is going to be the vector direction. AZ would be, the vector sense would be minus 2 would be, and the minus A is minus 2 times AZ. Do y'all follow me on this, class? Just give me a show of hands if you do. Well, I shouldn't say 2, minus Z AZ, pardon, minus Z AZ, because it's located at some Z. We don't know what Z is yet. Y'all with me? Okay, now, the only thing you have to do here is I've already made the sense vector here, and now you can see. Let me erase that and that, and look over here. I have 2 over 9, because that was 3 squared, is equal to the Z, positive Z coordinate over this, which is going to be what? This is going to be just this z squared. I'm sorry. This is a unit vector. Do y'all follow me in this class? The only thing I did is equate the force, or the electric field. The electric field from this has to be equal in magnitude, opposite direction from the electric field from the actual charge that was placed at -3. When you do this, what do you see happens here? You get what? Z squared is equal to what? Well, it's 9/2, right? Or z itself would be 3/square root of 2. And that would be the position. Do y'all follow me? How many see this right here? And again, the key is just realizing that the electric field from this has to be equal in magnitude, opposite direction from the electric field from the other one. Can you all follow me? By the way, that was 3. You'll notice this is less than 3. Think about it. The electric field is proportional 1/r², right? We had 20 nanocoulombs here, and we had an electric field at a range of 3 meters. Here we have 10 nanocoulombs. In order to have the same electric field strength, R has to be less. Do y'all follow me on this? And that actually is the answer. Okay, that was just a simple illustration of how you would go about reasoning through and calculating. That's it. And you can do it for any number of charges. You can get the electric field. You can find the electric field needed to cause the total electric field, or the charge needed to cause the total electric field to be 0. Now, the next thing I'm going to do, how many are familiar with Cartesian coordinates, x, y, z? I hope the whole class. How many have seen cylindrical coordinates? All right, we're going to use cylindrical coordinates to get the electric field from a line charge. These are classic problems, and if you've had physics here, you've seen this, but I want to review it. It is classic. And I might add that a lot of these problems that we're going to be talking about right now, or at least the charge distributions that give rise to electric fields, they're classic. You have to know these. Basically, you're going to get very familiar with them. So the first one is a line charge. And we're going to start by saying we have a line charge on the z-axis. And before I do that, let me just say, if you have any differential amount of charge, if I just have a charge dq here, and I'm at a distance r away, and I want the differential electric field. The reason it's a differential electric field is because a differential charge is causing it. That's it. You all follow? Same exact formula as before. You can say this is equal to dq over 4 pi epsilon naught. Then take the magnitude of r vector squared in the AR direction. Again, AR would point away from the charge, and it would be in the direction of the point of observation. The electric field don't have the value of 1. You all follow me in terms of magnitude? Everybody good on this one? All right, so this is the differential electric field. So when we have an infinite line charge, it has a charge density rho L. That's just coulombs per meter. Now there are 3 charge densities you've seen already before in physics, but you've seen charge densities that are line charge densities, or basically you've just seen point charges, Q, right? In coulombs. Then you've seen line charges, that's coulombs per meter. How much charge per meter is there? It's a density. Then you've seen surface charges that are coulombs per meter squared. And you've seen densities that are coulombs per meter cubed. That's volume. It really just has to do with the density of the charge. So if we have this, and we're going to use the z-axis like Wentworth's book does, just be attentive to this. I know you've seen it. It's nothing new under the sun here, but you should be attentive. Make sure you don't miss details. So I want to know what the electric field is. First of all, let me make this argument. If this, we're assuming it's an infinite line of charge. It goes on forever. If it's infinite, doesn't matter where I am on the z-axis if I come out a distance rho away to measure the electric field here. This is what I'm after. At a given distance rho away, class, think, it's infinite. If I move up or down, it still looks the same, right? There's absolutely no change. The electric field will be a function in magnitude of the radial distance away, and that's labeled as rho. So what I'm trying to show you is we're going to go out a distance rho, and rho is measured, by the way, from a perpendicular to the line charge, all right, from there to the point of observation. So that is rho, and it is the vector r. So now we come on, and I'll get to this. I want to make sure I hit everything. All right, that's the distance away. So if we have a little chunk of charge here, call that dq. And let me try to get a different color mark if I can, if they work. Well, I'll try it. I come out to this point here, and now I want the differential electric field caused by this differential charge. You all follow me? Now remember, the differential charge that we're going to get has to do with the line charge that has rho L as the charge density. So dq right here is simply equal to rho L dz. Does this make sense to everybody? Rho L is in coulombs per meter, dz is in meters, so you get coulombs. It's a small amount, right? Now I say, what is this differential electric field? Let me use the black mark for this. Well, first, before I get this, I'm going to assume this is at 0 because it's infinite. If we're at a height z here, y'all with me? I've got a z coordinate and I got a rho coordinate. Rho is just the radial distance, and if you look, you'll notice that rho is really square root of x squared plus y squared if you had Cartesian coordinates. Do y'all follow me, class? How many understand that, please? All right. Come over here. What is the differential electric field? Well, technically, it's dq. dq is this, so it's equal to rho L dz. Then I have to divide that by 4 pi epsilon naught. Some of you will use k there. You just have 9 times 10 to the 9 because it's easy. All right, but I'm doing this in the formal way that's in this book. Now I have to put r squared. So next, what is r? I want you to take note of this. Ask yourself this. Who knows? What is the distance from here to here, vector distance? Well, let's start with the rho differences. The rho differences here is rho, right? What's the rho difference here? 0. It's on the axis, right? So it's rho, a rho. A rho is a unit vector in the radial direction. Everybody with me? Next, I want to find, is there any reason to add phi in here? Think about it. Your gut feel is right. Phi loses meaning if we're right on the z-axis. I mean, it doesn't matter what phi we're at. I mean, if you look at this, it has no bearing on the distance at all. Does it, class? Not at all. So we ignore it right there. But what about z? Yeah, z does. My position here, I mean, the position here is 0, isn't it, class? Z equals 0 minus this z, so it's going to be what? Minus z, right? And here's how you always tell. This is the vector direction that r would be pointing. You see it's got a negative sense in the z direction, positive sense in the rho. Everybody good with that? All right. So that's r. Now I need to find out what magnitude of r is, and that's simply what? They're orthogonal, so it's rho squared plus z squared to the 1/2 power. Y'all give me that, class? The square root of that. Everybody agree? I'm going to do on that one. All right, so I need to take r squared according to this formula, so that's just what? Rho squared plus z squared. The 1/2 goes away now, doesn't it? Now I have to take that and multiply it by a unit vector ar. What is ar going to be? Take a look at this, guys. I know it's Friday. Work with me on this. How do you get the unit vector? You get r vector over magnitude of r. You agree, class? What is it? That's r vector. So it's equal to what? Rho a rho minus z a z over the square root, or really, instead of square root, let me just put to the 1/2 power. It's really equal to rho squared plus z squared to the 1/2 power. Does everybody agree that is a unit vector pointing from the source point of the charge to the point of observation? How many do? Some people are bored to tears. Oh, they've seen it too many times. Are you all with me, class?
Here's what I'm going to do down here. I'll just make this 3/2 because I've already got the thing I'm looking for. If I multiply it by, the same thing to the 1/2 power, it's 3/2. Then I put the values down. So this is going to be equal to A rho minus ZAZ. Everybody so good so far? All right, that's differential. Now, we want the total electric field. So to get the total electric field, what do we always do? Think of the building block approach. Find the differential field, and then do an integration to find the total field. That's always the way you were taught in physics. And when you had your calculus courses, you find the differential volume to get the total volume, you integrate over all the area or over the region it existed. Same with the electric field. Now we integrate this differential field over the region the charge exists. So when we do that, it's going to go from Z, since a dz integral, z equals minus infinity to infinity, and we will get the electric field. This is in your book, and this is a very classic problem, by the way. Now this would be the electric field from an infinite charge, infinite line charge. You all agree with this? Now, a couple of comments that are important. This is the way Whitmer's book does it. He makes this argument. He says, I've got a charge here. Remember, rho L is not a function of position. If I come down the same distance, all right, same distance below this point, I'm going to have another charge that would have the same magnitude. Y'all give me that. And if I drew a radial vector here, that radial vector would have the same magnitude. The difference would be the z-coordinate would now be positive, right? It would be ZAZ. Y'all follow me in this class? And if you looked at the differential electric field from this one, right here, you can see one thing, that the vertical components will cancel. How many see that? Y'all with me? The vertical components are going to cancel. So, and Whitmer does this a lot, and it's actually, if you can see this, it's smart to do it. If you can't, you got to do both intervals. So what I'm going to make the claim that there is no z component of the electric field here because of cancellation or symmetry. Whitmer's book will use arguments of symmetry. It's basically the engineering way to do it. Anytime you can reduce the number of calculations, do it. All right, but make sure you're allowed to do it. And you can in this case. So that means there ain't no z calculation needed. Do y'all hear me on this one? So normally we'd have to integrate this term with rho A rho and then integrate ZAZ. And you would have to do that if it was a finite length line. All right, you'd have to do that if you weren't centered right at the center. Do y'all follow me, class? However, for this particular problem, we can get rid of this. All right, so now we have this. Can you all follow me? I'm going to take a moment. I'm just going to expand on this, and then I'm going to make a comment, because there's going to be people that worry about one thing in a second. And I'll tell you, you don't need to worry about it, but I'll tell you why. So this is going to be equal to rho L. I'm taking out all the constants over 4 pi epsilon naught. And now I'm going to take out the rho A rho out in front. And now I'll go ahead and put the integration. Here it's from z equals minus infinity to infinity. And if you look at this, I have simply dz over rho squared plus z squared to the 3/2 power. This is the thing we need to evaluate. Can you all see that, class? Because it's a dz integral. That is the thing that's a function of z inside the integration. Everything else are constants, right? That don't vary. Y'all follow me? How many see this right here? How many know what that integration is? If you don't feel stupid. All right? I gotta look these things up every once in a while too. It doesn't matter. I would give you this integration, but I'm going to level with you. Nowadays, your calculators do symbolic integration. If you have a computer, you got Wolfram Alpha, you got tables. Everything you need to figure out an integration is available to you. You still need to at least have an appreciation of how to set the problem up. Now that integration is the classic. It's one of the classics. By the way, do you remember how to solve this thing?
You have to use like sine or tangent.
Trig identity. Yeah, anytime you have things that look triggy, you use a trig identity. Don't worry about it. I'm just going to get to the root here. So anytime you have, this is going to be, I think it's of the form of dx. It's in the back of his book, and this is an x squared plus a squared to the 3/2 integral. What this boils down to is you're going to have 1 over a squared, and then it's going to be x squared plus a squared to the 3/2, or to the 1/2 power, pardon me, 1/2 power. You can check me on that, but do you remember that type of integration? It's in the back of his book. He has integral tables. Can anybody check? I think he uses he uses the x and a symbols, by the way. If you got the book, take a look in the back. It's in like appendix A or B. All right, so that means this thing breaks down to, let me come down here and do this. E from that infinite line charge is going to be rho L, then it's going to be rho A rho over 4 pi epsilon naught. And then you have this business. You're going to have, after all is said and done, 1 over rho squared, and it's going to be there's a z up top here. There's an x up top, my bad. And it's going to be z over z squared plus rho squared to the 1/2 power. And it's evaluated from z goes to minus infinity plus infinity. I'm just rewriting this thing down here. I forgot the x on top. Can anybody look in the back and see if that's right?
Yeah.
All right, what page is it on?
623.
In Whitmer's book. Okay, 623. All right, now if you look at this, if you follow me on this, take a look at this right here. This here. All right, what is, when z goes to infinity, what do you see? Look, I got z going to infinity. That is got basically infinity to the first power. Then I got infinity squared 1/2. This is infinity to the first power. You all see that? This is going to 1, so this itself is going to go to 1 over rho. You all see that? 1 over rho squared, pardon, right? Then it's minus when z goes to minus infinity. When z is minus infinity, there's a minus infinity here over infinity squared to the 1/2, where you get another value of 1, right? It's 1 minus minus 1 or plus 1. So the whole thing boils down to the E field from this, and I'll put it over here, from an infinite line charge will be equal to rho L. Instead of 4 pi becomes 2 pi epsilon naught rho A rho. And I have plenty of comments about this. So that's the electric field from a line charge. An infinite line charge, it's proportional to the distance away from the axis of the line charge, and it's in a direction that is perpendicular to the line charge. Do you all see this? Now, I'm going to show you some things that aren't that clear right now. Everybody got me on that? You can go through the integration, and again, we could make it a finite length charge. We could do all sorts of permutations, but the essence of how you solve it, start with a differential electric field, then go ahead and integrate that differential electric field over where the charge exists to get the total, and it'll always work. Okay, now let's take a look at this applied to some problems that people mess up. And what I'm doing is I'm telling you where you have trouble, where historically people really botch these things. And let me go a step further too. And say, now it's important to hear me on this. This A rho symbol that I have here, right, this is going to be 2 pi epsilon naught rho A rho. The rho there is the perpendicular distance from your line charge, that's infinite, to the point of observation. It doesn't matter if the line charge is in the z direction. It could be in the x direction.
It could be in the y direction. It could be in any direction. Do y'all hear me? As long as it's infinitely long. So this is clear. This is important. That is the distance from the center of that line charge to the point of observation of the electric field. The second thing is a rho is a unit vector that has to do with that radial direction. Now, the best way to see this is for me to show you the thing. Show you why it's a problem. You all ready? Now watch this. This is important because this is where people make mistakes historically all the time. So let's do it this way. Here's my coordinate system. Write this down. It's not in the book. All right, X, Y, and Z. Now, I'm going to say I have an infinite line charge, and the infinite line charge is at y equals -2, and at z equals 0. So this is rho L. And this thing is infinite in the x direction, so it's at y equals -2. That's the origin, that's 1, 2 down here, right? And it's at z equals 0. So I get an infinite line charge. Can you all follow me in this class? Just assume you took the infinite charge on the z-axis, you moved in the xy plane, and you shifted over to x or y equals -2. Can you all imagine this? Now, let's say I want the electric field from this infinite line charge at a height 3. Y'all with me? Now, I know this would be the perpendicular. This is rho vector. I'm going to show you, I'm going to do this to make it easier for you to see. I'm going to look right down the x-axis and regraph that so you don't have that perspective problem. If I look right down the x-axis, this is still y and this is still z. Here I'm out at -2. Here's my line charge, rho L. Can you all imagine that? We're going right down the x-axis. Everybody with me? Now, I said I was up 3. It could be any distance, but I chose 3 for a reason. This is 2, and that's 3. So now I draw this out here. That is my vector rho. I know in Whitmer's book, rho is a coordinate dealing with cylindrical symmetry, assuming x, y, and z correspond, or excuse me, assuming the z-axis and rho and theta correspond to the x, y, z axis. In this case, you dismiss it. Y'all follow me on this? This rho has to do with the distance, the perpendicular distance from that line charge to the point of observation in the electric field. It's still an infinite line charge. And now I want to get the electric field here from this. It points radially away. Do y'all follow me, class? So I need to get rho vector. What is rho vector? Just look at it. Well, dimensionally speaking, what is the y distance? Here, y is what? Class? Can you all see this? This is y. What is y right here? Just tell me.
0.
What's y here?
0.
0. All right. 0 minus what? A -2. Correct, class? That's a +2 ay. Do you agree with that? What about z? What's z here?
0.
And what's z here?
3.
3 minus 0 is 3. So it's plus 3az. Y'all follow? All right. We're almost there. Now I need to get a rho. All right. A rho is what? 2ay plus 3az over what, class? Square root of 2 squared plus 3 squared, right? Isn't that right, class? Square root of 13, right? All right, but that's it. Do you agree with that? Now, come over here and write the electric field, or I mean, get the electric field based on this. So that's rho L over 2 pi epsilon naught. That's magnitude of rho. That's that. So it's really 2 squared plus 3 squared to the 1/2 power. But you can see when I multiply by a rho, then I get what? I get 2 ay plus 3az, and it's divided by this again, so I can get rid of the square root. And that's what I'm about to do. And that would be the electric field. You'll notice it has a y and a z component. Do y'all follow me? Now, here's the problem. The minute you think of the electric field from an infinite line charge, you think cylindrical coordinates only. Y'all follow me? It doesn't mean that. Rho is the distance, magnitude distance from the center of that line charge to the point of observation, and a rho can be in any coordinate system. Here, it's more appropriate to use y and z because it lends itself to the axis. All right? This thing's right along the x-axis. Y'all with me, class? Now remember what I tell you about this, because I promise you on tests, people mess this up all the time when I ask for the electric field from a line charge, surface charge, and point charge at a point in space, usually the z-axis. They mess this one up like I can't even imagine sometimes. And they come up with new theories that aren't true. Anyway, I'm giving you a warning. I hope you heed my warning. Okay, next we're going to do the loop. Do you remember this in physics, this right here? How many do? You don't? Line charge? I don't know if your physicist, the physics professor went into that, if it's in any direction what happens, but that's the way you get it. Depends who you have. And, physics and calculus and differential equations and linear algebra, they're really the underpinnings of everything we do. We apply all that stuff. And you have to really be good at this to be a good engineer. And there's so many people that fail out because they have one or two weaknesses, usually in differential equations or in calculus. I mean, one of the, okay, I guess differential equations technically is the differential calculus. So next we're going to do the loop of charge, or the ring of charge. And again, these I call them building blocks. Most of the time we can find any system that we're going to talk about, we can say can be decomposed into these things and find the differential electric field from these things and then integrate that to find the total electric field. So for a ring of charge, what we're supposed to, he puts it on the x-axis. Let's see if I get a marker too. So call this x, call this y, call this, let's try it. Got a bunch of them over here, maybe they work. All right, this one looks good. Now we're going to have a ring of charge, or a loop, centered in the xy plane, and it's going to look like this. I'm trying to show you in the xy plane. Do y'all follow me? What page is it in the book, by the way?
138.
This is page 138. This markers. Anyway. Okay. Actually, this one's not. All right. Now, I'm going to assume, I know he uses A in the book, but I'm going to call this rho. That's the radial distance from the origin to the radius of that circle or that loop. We're going to assume this loop has this charge density on it equal to rho L. Y'all with me? A couple of tricks on this one. Be attentive. Now what I want to know is the differential electric field on the z-axis at any height z. So I'm after the electric field from that from a differential chunk of charge. Can you appreciate this, everyone? So I'll just say that I have a differential chunk of charge here. That's dq. Now dq technically would be the charge density, rho L, times the differential length, right? Now this is a curvilinear system. So this is important you see this. If I take a look at something that has a radius r pinned here, and I move over a small angle, call it d phi, the length I move here, dl, is equal to r d phi. I want to make this point. This is like a windshield wiper, if you will. Think of the tip. All right. The tip moves a distance proportional to the length of the wiper times the differential angle. Do you all remember that? It's rho, or it's the distance, d phi would be the differential length. The larger rho is, the larger the actual d phi would, or the actual dl would be. Do you all see this? How many of you see this right here? All right. So now I can say that this dq is really equal to rho l times the radius distance rho times d phi. That would be an angle. Now I write down the differential electric field here. So I need to do this and show you this vector r. And that's from the differential charge to the point of observation E field. You can see one thing, it's going to point away from this. So this would be the differential electric field. You all see this, class? With me? Far back, can you guys see it? You're way back there too. I can't see. I'm back there. So that means the differential electric field from that is equal to dq, and I'll just write this down. So it would be rho L times rho times d phi. Then we're going to divide it by 4 pi epsilon naught. Now I need to get r. So just take a look. Try to visualize this. What is the distance from here to here if we do it in cylindrical coordinates? Well, the position here radially is 0, isn't it? If you're on the axis, I have 0 minus rho. So this is going to be, for the radial direction, it would be minus rho a rho. In other words, it's pointing in the opposite radial direction as this point. Now there's going to be something that bothers you about this, and it bothers me too, and I'll explain it. What about z? Well, it's going to be plus z-a-z, right? Because the position here is at z, and the position here is on the xy plane, or z equals 0. Do you all agree with that? There is no reason to talk about phi. It loses meaning. We're on the axis. Phi has no meaning on the z-axis. Y'all follow me? Don't even worry about that. So that's r, and if I go down here, I know I'm going to have this squared, magnitude of this squared, which is just going to be rho squared plus z squared. Now I have to multiply that by a rho. Do you all follow me in this class? Or ar. Agreed? Again, ar is just that vector divided by the magnitude of that vector. So if I go ahead and do this, that vector would have minus rho a rho plus z-a-z, and then divided by the magnitude is really dividing by this to the 1/2 power. So I simply put this to the 3/2 power. Y'all follow me on this, class? Remember, that's a d phi integration. Now I'm going to tell you the way Whitmore's book does it, and then I'll tell you another way to do it. So that's the differential electric field. If I wanted the total electric field, if I took this and integrated it around the loop, this would be the total electric field. If I took this and integrated it from phi equals 0 to phi equals 2 pi, I would get the total electric field, E in the z direction. Does everybody agree with that? In other words, here's how Dr. Whitmore talks about it in his book. He says, and I appreciate this, because he's an engineer. Engineers always try to reduce the complexity if they're smart. Complexity of things. Don't ever do calculations you don't need to do. Don't make trouble for yourself. So if I look at this, and here's his argument, I can see that, well, this has an electric field that's got both a vertical and a radial component, right? So go to the conjugate point. Conjugate point is just draw a line from that differential charge to the center, 0, 0, 0, to the other side. And I'm going to have the same magnitude of dq here, if you look at it. Do you agree? And that's going to give an electric field too. And that electric field will have the same vertical component, but the horizontal components will nullify themselves. How many see this? I see. Trust me. Do y'all see it or not? Just think about it. It's very important that you see symmetry like this. Now, you don't have to do that. You can do the formal integration,
but you can't do it in these coordinates. You have to take you have to take a rho, and you have to take a rho and turn it into, I'm just going to mention this, if you take a rho and turn it into cosine of phi ax plus sine of phi ay, that is, believe it or not, a rho in terms of an ax and an ay vector. All right. If you do that, and you take that and plug it into this equation right here, rho is going to be a constant. That's just the scalar radial distance. And then do the integration, you'll find out you get the same thing. I might as well do this just for the sake of clarity. So y'all agree that's right? Okay. Now, what I'm going to do is say, therefore, EZ itself will be equal to, and I'm going to take all the constants outside. You see how rho is at a constant radial distance? It's the ring's radius. So I can take rho L, and I can take rho outside. I can take 4 pi epsilon not outside. Notice what else I can take outside. You see how this doesn't vary? It's fixed. Z is fixed, rho is fixed. That comes outside too, which is nice. So that means this becomes rho squared plus z squared, right here, to the 3/2 power. And now I'm going to go ahead and say that here I'm going to have two integrations that I have to deal with. I'm going to put the AZ first, so I have Z, AZ, and I integrate that d phi from 0 to 2 pi. We'll get to that, and that's still an AZ. Then I have minus rho times the integral from 0 to 2 pi. And here, a rho becomes simply cosine of phi ax plus sine of phi ay. And we do this d phi. Now, I know I'm a little over, but just work with me, all right? Y'all follow me on this? Tell me about this integration, anybody. What happens when you integrate cosine phi? What do you get? Minus sine phi, right? What is minus sine phi evaluated from 0 to 2 pi? What's sine of 2 pi? 0. What is minus the sine of 0 is 0, right? What's the integral of a sine? A cosine, right? And when you do this, what do you always get? 0. Anytime you integrate a sine or a cosine over an entire period, the area above is the same as the area below, you get 0. This goes away completely. That means this is the only thing left. Y'all follow me on this? When I integrate this from z is not a function of phi. When I integrate this, I simply get phi evaluated from 0 to 2 pi is 2 pi times that, which means when all is said and done, and I'm going to finish here, the E field on the z-axis from this loop right here, if you look at it, I'm going to get 2 pi here, and it'll cancel that 4 pi. So, I draw it right. That means EZ is going to be equal to rho L times rho, O times Z, by the way, times Z. And it's going to be divided by simply 2 epsilon naught. And it's going to be rho squared plus Z squared to the 3/2 power. It's in the AZ direction. I have one comment about it, 2 comments about this. Do you all see this now? What page is this on in the book? I just put rho. I'll do this. I'll try to make this neater. This is really what? Rho L times the radial distance rho and times Z, right? Something to know. What's the electric field when Z is 0? Just look. 0, right? Look, Z's on top, right? If you notice that, you'll notice one other thing. What happens when Z is negative? The electric field becomes negative. My point here is the electric field from this, that if you're below the XY axis, it's in the negative direction. If you're above it, it's in the positive direction. You'll notice one other thing. As Z goes to infinity, as we go infinitely away from this, it goes to 0. There's a finite amount of charge on it, right? Anytime you have anything with a finite amount of charge,
If you go to a distance of infinity away from that, it will always go to 0. If it doesn't, you made a mistake. That's a calculation check. Y'all with me? All right, I've spent too much time on this. I'm going to give you some homework. Please do it for Monday. I was going to give you a quiz Monday. I'm a little resistant based on today's performance, but what I'm going to do is this. I'll go over this stuff, and on Wednesday we're going to have a quiz. Guaranteed, but I encourage you to do it. If you try cramming, because I'm going to cover more material, probably going to get real trouble. I'm only doing this because this is a homecoming weekend, too. I got kids bugging me about it. Yes.
What happened to pi in the last step?
Remember when I hit right here? I go from 0 to 5. I got 2 pi and I got 4 pi.